So under this training, we are going to see the different components that makes up the process instrumentation and how these various components interact together to make sure that process is operated smoothly and reliably. So those instrumentation components, how we are going to improve the reliability is what we are going to conclude this particular training with. So to assist us in achieving all of these that we have just said, we have broken down this training into a series of topics or sections, okay, that will make us to appreciate what process instrumentation is. So the first, we are going to introduce ourselves to industrial instrumentation. So we are going to see these various components and also what this component they do in instrumenting our process. So we are going to look at the process variables, and as you well know, these process variables, as we'll see later, they are process parameters that changes with process conditions, okay? So if these variables are not properly controlled, it becomes very difficult for us to control or achieve the desired outcome of our process. So you see that understanding of these variables and what can affect or what could affect these variables is very important for us to ensure the reliability of our process. Then we are going to see process control, three basic types of process control that we have. We are going to look at them briefly. And then we are going to look at some of these components of our process instrumentation. So we are going to look at the final control element, valves. Okay, remember we have discussed process variables and sensors, okay, which are actually a component in the process instrumentation. So the final control element, valves, okay, we are going to look them, and the accessories on valves, the actuators and the positioners. We're also going to look at them, discuss them in details under that section, valve actuators and positioners. And then finally, to ensure the reliability of these various components in the process instrumentation, we need to calibrate them. So what does it mean to calibrate? Okay, and if these components are out of calibration, what does that also mean, and what we need to do in order to return them to calibration of functional status as so desired. So those are the various sections that we are going to cover under this training. So let us go straight into the first part now, which is the introduction to industrial process instrumentation, okay? So first, what we are going to look at is industrial process. So what is an industrial process, okay? So as you can see on the right of your screen, industrial process is a series of steps, okay, that you need to undertake in order to get your final output that constitutes your process in that industrial environment. So we can say that process, as used in the terms of process control and process industry, it actually refers to the method of changing or refining raw materials to create an end product, which means what we are talking of at this stage is a series of steps that you need to take in order to change the raw material that you have into a finished product or an end product. That is the process, okay, industrial process that we are talking about. So this process industries where these industrial processes takes place. They include the chemical industry, okay, where chemicals are produced, where raw materials are put together to produce chemicals for domestic use and also for industrial use. Okay, so we have different types of chemical industries. As you can see, we have the petrochemical industry, we have the paint industry, and what have you. Then we also have the oil and gas industry. So the oil and gas industry, as well known, is made up of the upstream, midstream, downstream. The production aspect, which is the upstream, where the petroleum is actually produced, we actually need to control the processes in order to get the specification of this petroleum that we actually need out of those processes. Then we also have the refining industry and also the marketing and distribution. So all of these section of the oil and gas industry, the processes need to be monitored and controlled. So we are going to see some of the variables that we monitor in these various aspects of the oil and gas industry. Okay, so as you can see here, this is a production platform where the crude is actually produced. So you see that in the production, we need to monitor some certain variables, and in monitoring these variables, we need instrumentation. Okay, so that we'll be able to get the desired quality and the desired output from that process. So we also have the food and beverage industries where food and beverages are produced. So the series of steps, which are the processes, we need instrumentation to monitor them, to control these variables so that the desired outcome from these processes will be achieved. So these are examples of process industry. Okay, so the process industry also include the pharmaceutical industries where drugs are produced, the water treatment industries where potable and industrial waters, okay, are also produced, as we can see. So this is an example of a water treatment plant. So here the water is meant to go a series of process. So for us to get the desired series of steps, which is the process, for us to get the desired output, we need to monitor certain variables, okay, and we need instrument or instrumentation on the system or on the process. So we also have the power industry, okay, where electrical power is generated. So the steps that are involved, the series of steps, which is the process, we need also to monitor and control all of this, and it is the instruments that will help us to monitor and control all of this process. So as you can see on your screen, so we have a reactor, okay, where radioactive fission or fusion reactions or reactive reactions, okay, takes place. And we know that those radioactive fission or fusion have energy, okay, heat energy as their byproduct, since they are highly exothermic. So those heat that is released is harnessed to heat up water, as you can see in a boiler. Okay, this helps to generate steam. So here we see the conversion of that heat energy that is as a result of that nuclear reaction in the reactor. That energy is converted to high kinetic energy in the steam, as you can see, and that fast moving steam with that high energy is directed towards the turbine. Okay, yeah, as you can see here, so at the turbine the energy is converted, the high kinetic energy in the steam molecules is converted into rotating mechanical energy. So that rotating mechanical energy is transmitted along this shaft that is coupled to an alternator or a generator that helps to convert that rotating mechanical energy into an electrical energy that is further distributed. So you see that in this process industry, our desired output is the electrical energy, and you can see that we have a series of steps, okay, in the production of electricity. One, the conversion of heat energy in the reactor to steam, kinetic energy in steam, the conversion of that kinetic energy into rotating mechanical energy at the turbine, and also to electricity at the generator. So if you look at all of these series of processes, there are some variables, as we will see later, that we need to control in order to achieve what we need to achieve to get the desired level, okay, of voltage or of power out of the power station. So you can also see that part of the process is the condensation of that steam, okay, back to water. So you can see here in the condenser, and then it is recycled back. All of these steps, okay, that constitutes the process of generating electricity need to be monitored and controlled. So as you can see, these are some of the process industries, examples of process industries that we have, okay. So let us still look at what we mean by process control. Process control. Remember, we said the process is a series of steps, okay, in the process industry that we need to take in order to get our finished product. So process control is the action or the process of using technology, okay, or instrument to control that series of events that we need to transform our materials into the desired finished product, okay. So that is the process control. So we also have process variables. As we said before, these are process parameters that changes with conditions of the process during normal operations, okay. So these process parameters, they have the capability of affecting the process and thus the output or the finished product. So we need to control these variables, okay. But first we need to appreciate them, what affects them, before we'll be able to control the variable. So these process variables, they are process parameters that changes during the process with changes in a process condition. Then process instrumentation is the use of technology or the use of instruments to monitor and control the changes, okay, in these process variables. That is, as these variables are changing, the technology or the instrument that we use to look at them as they are changing, and then to readjust them to the point, the level that we want them to be, okay, so that our process will bring the desired output. That is called process instrumentation. So we are going to see more details of it later, okay. So let us also look at the types of process industries that we have. We have basically three types. We have the continuous process. This is the process industries where raw materials are continuously fed into the process and products are continuously removed from the process at the same time. A good example is the power industry that we saw earlier, and the refining and petrochemical industry. So like in this power industry now, you see that the water is continuously fed, okay? Since we have continuous heat generation at the reactor, so steam is continuously generated also, and power is continuously given off or generated. That is the product of this process. Okay, so this is an example of continuous process because the various steps are undertaken continually, and our output is gotten out of the process continually also. So you see that we continually feed in the raw materials, okay, what is needed to produce our desired output, and we continually take out the product of the process. So that is a continuous process, okay. Then also too, like in the refining too, the distillation process is also a continuous process. So you see in it that we continually feed in crude into the distillation column and continually take out product at the various draw of points. Okay, so you see that the crude is first preheated in the heater. Okay, it is heated in the heater and then it is sent into the distillation column as you can see. Okay, so the parts of it that has been evaporated or vaporized will rise up the column, and as they rise up the column, they are cooled at different trays. So, and this is done with respect to the boiling point of the various products, okay, in the crude. So at the draw off point, we have different products as you can see. So all of this is done in a continuous process. Okay, it is done continually. So this process is termed continuous process in that raw material is constantly fed into it, that is crude, fed into the heater and then into the distillation column, and products, gas and what have you, they are constantly drawn off, okay, from the distillation column at various points in the distillation column. So we also have the batch process too, okay. So in the batch process, materials are added in a vessel at a particular quantity and measurement, okay. They are added in a vessel, then a process is meant to take place. At the end of that process, the product of that process is now moved to another process, and then maybe other materials will be added or it will be subjected to a different condition, okay, to generate another product from that process. So as you can see here, you see that products could be sent into this vessel or tank, then they blended together, mixed for some time, okay, subjected to certain condition, maybe heating or pressurization, okay. Then after it has been subjected to that condition, a product will be formed from this process, okay. Then it can now be sent into another process, and as it's sent into another process, other raw materials, okay, are added as you can see, and then the mixture could be subjected to a different condition that is different from the condition it was subjected to here. Okay, so you see that the process is going on in batches, and we expect that a specific product should come out from one batch, okay, from each batch, and then they are sent to another batch subjected to a different condition until we finally get our product out. So a notable example of industry that is engaging in this kind of process, this batch process, is the beverage or beer industry or the soft drink industry, okay. So you see that the raw materials could be mixed at a certain stage, heated at a certain stage, filtered at a certain stage. Other additives may be added at different stage. Then the corking, as you can see, filling of bottles and filling of the bottles or the can, and then the corking will also take place at different stages. Okay, so this is called the batch process. You must finish one stage before you can go to the next stage. Okay, so we have the discrete process or discrete manufacturing process, where a component of the finished product is subjected to a complete manufacturing process or production process. Okay, which means that separate components, they are produced in different processes, and then those components, they are brought together and assembled together. And a good example is the automobile industry, where cars are manufactured. So you see that the engine, they are produced elsewhere. It could be that these various companies, they may be produced in by different companies in different countries. Okay, the engines may be produced elsewhere, the windshield produced elsewhere, all of these wipers and what have you, they could be produced elsewhere also. The tires could be produced elsewhere, the headlamps, they could be produced elsewhere. Okay, so these various components at the end will be brought together and then assembled to give us what you are seeing on the screen. So that is the discrete manufacturing process, and the automobile industry is a very good example of the discrete manufacturing process. So still on the introduction, we are going to look at process control. Okay, so process control, they can actually take two forms. First, the sequential control, which means that one step will come after the other, okay, or one stage will come after the other. That's the sequential control, as you can see on your screen. Okay, you see that in this sequential control, you see that liquid A is allowed to flow into the tank A. Okay, then the liquid B will be allowed to flow into tank B. Okay, so this various flow is monitored by this sequencer. Okay, you see the sensor, which is definitely a level, which means that a certain level must be attained in this tank, and a certain level in tank A and tank B. Okay, before they will be allowed to flow into tank C for the next process to start. Are you getting me? So it is possible that this liquid A or fluid A will be subjected to some condition in tank A, while B can also, it is also possible to that it will be subjected to some condition in tank B. But if they don't attain this level, probably for proper blending or for us to have the desired ratio of mixture, okay, of the two products A and B to give us C, you will see that this this valve and this particular valve, C and D, will never open. So when this process, okay, has been completed, then these ones will open and then it will be discharged into tank C. And then the process that is needed here, probably the mixing of the mixture, okay, and subjecting it to other conditions also, will now take place. At the end of it, we can now have our mixture out, that is the product from this step. So what this means is that if this step is not complete, or this step is not complete, we cannot come to this step. So it is a sequential control system. Okay, A and B must be complete before we can move to C. Okay. So we also have the continuous process control. Okay, in the continuous process control, what that does is that the process variables, they are monitored continually. Okay, an adjustment to the process variable is also done continually. So this is simple continuous process like what we have in the level control in a tank. So you see that this is the sensor level switch. We'll see it later. This level switch, when the fluid in the tank drops below a certain level, it will energize the coil of this contactor, and then the contactor will close power, okay, close power to the pump motor, and then the pump will continue to fill the tank. Then as it is filling up, the level switch will be rising, and as it's getting up, it will get up to a stage, it will trip or cut off power to the coil of this contactor, and thus trip or cut power to the pump motor, which will eventually stop filling this tank. So you see that at times the tank is, once demand is on it, it will be going down, and then it will go down to a stage. The pump motor will come on and then fill the tank. It will fill to a stage, it will off. So the process is continuous, okay, without the intervention of humans. Okay, so it is done automatically. So this is a very simple continuous process. We also have other very complex continuous process control. We want to look at some typical continuous process control. Okay, a typical continuous process control is that of the production of steam. Okay, production of steam, where the water is fed continuously into the boiler, the steam is generated continuously from the boiler, and then that steam is sent into the process. Then chemical reactions, separation, waste treatment, distillation processes, as we saw in the case of the petroleum refining industries. Those are examples of continuous process control. Okay, so in all of these processes, like we said before, there are some parameters that varies or changes with condition of these processes, and these parameters, as they change, they have the capacity to affect the outcome of the process. And once the outcome of the process is affected, what it means is that the desired output from the process may not be achieved, or will not be achieved. Okay, so these parameters that varies with process conditions that can affect the process, they are called process variables. Okay, so we need to appreciate them, how to monitor them, and how to control them, and what instrument we need to use to monitor and control these process variables. So as you can see, we have pressure. Pressure is a process variable or process parameters that can change oftentimes with changing process condition, as we'll see later. We have temperature, we have level, okay, we have flow, we have position, okay. Then we also have force, we have density, viscosity, sound, we have even the pH, okay, of the process. All of these, they can change with changing process conditions, and they can affect our process or the output from our process. Okay, so we will look at them in a little bit details later, especially the most common process variables, the pressure, temperature, level, and flow. So it actually depends on the process that you are looking at. Okay, some of these parameters in a certain process could be more important than some other parameters, okay, or variables. So in some processes, maybe it is only one variable, maybe temperature or pressure, that has the capability of affecting our process, and thus that is the only variable we'll monitor. Okay, while in some, maybe it is the pH, so which means that it is the pH of our process that we need to look at, because as the pH is changing, it can affect our process, affect the outcome of our process. Some is the viscosity. So, but for the sake of this program, we are going to look at the most common process variables, which are the pressure, force per unit area, temperature, the degree of hotness or coldness, the level of fluid in a vessel, then the flow. Okay, the flow rate, volume per unit time that goes through a specific section of the process. So those are the ones we are going to be looking at in this program. But all of them, as we'll see later, we have instruments that are used to look at them. They are called sensors. Okay, we have sensors for pressure, temperature, level, flow, position, force, density, viscosity, sound, and the pH. Okay, so we have the sensors. Then we also have instruments that will help us to magnify the output from these sensors. Okay, and then that can also compare it to a set point. Okay, so those are called the controller, and then maybe that can send it to wherever we want that information to go. Okay, that's where the transmitters will see later. So we have all of those, and then if there are adjustments that need to be made to the process, the information could be sent to the final control element. What those final control elements are, we'll see them later, so that the necessary appropriate adjustment could be done to return that process variable back to what we feel is normal. Okay, so here we have different variables that we need to be looking at. Okay, there are, like we said earlier, there are some variables that are more important to a particular process than others. So that variable that have that strong effect on the process, they are the variables that we monitor. So let's take, for example, this process on the left. Okay, so where fluid is continuously fed into this flash drum. So definitely, as the fluid is fed into this flash drum, the fluid is coming at a particular pressure. So in the drum, it is subjected to a lower pressure. So which means that some of the volatile components in the fluid will be flashed out. Okay, they will go into the vapor state, and those vapor will rise up, while those that did not flash out, okay, those that are still liquid, will remain in the liquid form and settle at the base of this drum. So it is a kind of separation process where you separate the lighter component of the mixture from the heavier component of the mixture. Okay, so the rate at which the feed comes into this drum will determine the level, are we getting it, of the part of the fluid that remains in liquid in the vessel or in the drum, and also determine the amount too that is flashed out that will form gaseous vapor, okay, in the upper part of the vessel. Definitely, if this level rises above a level, you see that it can affect the balance in the drum, okay, assuming it goes beyond this level. Of course, the rate at which it will be flashing or coming into the drum to flash will adversely be affected also. Okay, so we do not want it to get to that level. So what do? We need to monitor this flow rate and control it. Are we getting it? So here on this leg, we see that the flow of our feed or of the process fluid is more important for us here. Okay, so we monitor the flow. Here we have the sensor that goes to a flow controller that controls the final control element that helps to adjust the flow rate into the drum. Then the fluid that is settled down in the drum, we do not want it to go beyond a certain level. Okay, so you see that the process parameter level becomes a very important variable, because as the drum is filling, the level is changing, it will be increasing. As you are drawing out, the level is also going down. Okay, so here we need the level sensor that senses the level, send a signal to the controller that adjusts the final control element, such that when it gets to the required level, this valve will open up, and then we will remove some of the fluid from the bottom of the vessel out of the vessel. Then remember too that some of the lighter end of the feed that are flashed out will definitely tend to increase the pressure of the vessel, okay, above the liquid. So as that is happening, the pressure here is increasing. When the pressure increases to a level, okay, we need to relieve the vessel of that pressure. So a very important parameter for us to get those vapor out is the pressure. So when you look at the pressure, there is a sensor here that sends signals to the controller to the final control element. So when the pressure rises to a level, it opens up, and then the vapor is taken out of the vessel, so as to maintain a balance that will allow our flow rate to be maximized or optimized, such that we have the maximum flashing out of the liquid that is sent into the vessel. Then when you look at the right, here we have a steam generation system. Okay, so in a steam generation system, the boiler is a very important piece of equipment, as you can see. Okay, so in the boiler, what happens is that the chemical energy that is contained in fuel is converted to heat energy, and that heat energy is absorbed by water, and then the water is converted to steam. Are we getting it? So in the mud drum and the steam drum, we need to maintain a particular level of water. Okay, so when you look at it, we have a level transmitter. This level transmitter sends signals to the level controller, and then the level controller sends signal to the IP converter, and then to the final control element, which is the valve that feeds water into the boiler. Okay, so as more steam is generated, this water comes down, this level sensor senses it, sends signal to the valve opens up and add water to the boiler, okay, the boiler drums. So that is the level at that stage. Then now we also have other, if the energy that is contained, the steam pressure is not high enough, okay, we need to increase the steam pressure. You see that there is a pressure sensor here, pressure transmitter, pressure controller, that sends signal to the fuel valve, as you can see, it's on the fuel line. Okay, send signal to the fuel valve to increase the amount of fuel that is sent to the burner, to increase the amount of heat that is generated here, and then the amount of heat that is absorbed, the amount of steam that is generated will also increase, and thus the pressure of the steam will be increased. So you see that at different points, different process parameters, they are important to us. So we need to monitor them, control them, so as to get the desired result from the processes. Okay. So we are going to look at the various process variables now. So the first one that we are going to look at is the pressure. Okay, pressure, as you well know, is defined as the force per unit area, the force exerted by fluid, either gaseous or liquid, okay, on the walls of the containing vessel. So that is the force per unit area. Okay, that is pressure. So as you can see also, pressure is have different units, okay, of measurement. We have the PSI, or pounds per square inch. We have the Pascal, okay. We have the Newton per meter square, Newton for force, meter square for area. Then we have the inch or centimeter of mercury, centimeter of water or of mercury, okay, or millimeters of mercury, millimeters of water, okay. Then we have the atmospheric pressure, ATM, okay. Then we have the torr, and also we have the bar, which is about 1.013 ATM, okay. That is atmospheric pressure, and that is equal to about 100 kilopascal in the metric system. So these are the various units, okay, that are used to represent this process variable pressure. Are we getting it? So we are going to see this pressure, what are the various sensors that could be used to monitor this pressure, and how these sensors monitor or help to monitor the pressure, okay. So that is what we'll be looking at. So pressure measurement, we need pressure sensors to measure the pressure in our process, okay. So as you can see now, this is our process. The sensor is down there looking at the process, okay, which means that the sensor is exposed directly to the process, and it is by means of that sensor that we are getting the pressure reading, okay. So we have different types of sensors for pressure. We have the pressure manometer, we have the Bourdon tube. We'll explain them in a little detail later. We have the diaphragm, we have the capsules, and we have the bellows, okay. And then we have the strain gauge. These are sensors that could be used to monitor pressure, or look at the pressure in our process. So let us look at the first one, which is the pressure manometer. The pressure manometer is one of the simplest pressure sensor, okay. It's just having a U-tube, both end open, and then subjected to the different pressures. Are we getting it? So like in the one you have on the left now, you see that the U-tube, assuming you have water or whatever fluid on it, both ends they are open to the atmosphere, okay, which means that the both ends they are subjected to atmospheric pressure, the same amount of pressure. So the force on this water column is equal to the force on this water column, okay? So which means that the level on each side of the tube will be the same. It is balanced. So that is why we have it here at the 0 point, okay? So it is calibrated to give us 0. So now assume that this end of it is now connected to a pressure source. Are we getting it? So which means that if that pressure source is higher than the atmospheric pressure, what will happen? You see that the force on this column will be higher, and that will move the fluid in the right column up, okay? So it will move it up to a stage where the height above the left column is exactly equivalent to the force that is exerted on the left column, okay? So that is how the pressure manometer work. So if you look at it, you will see that the water on the right have been displaced, okay? Then the distance between here and here is about 2 units. Are we getting it? So that could be calibrated to give us the direct reading of the pressure. So if each of this is an ATM, 1 atmosphere, it means that we have almost 2 atmosphere here. That will be equal to the pressure of the fluid that this end of the manometer is subjected to, okay? So that's the pressure manometer. So we also have the Bourdon tube. The Bourdon tube is just a tube that is capable of expansion when the pressure, internal pressure is increased, okay? So what this means is that there is an opening here that goes into this tube. So once the pressure is administered into the tube, you see that it has the effect of elongating this tube, stretching this tube. So as this tube is stretched, since it is connected to the spindle, you see that the spindle will move. And this scale have been calibrated, okay, to give us the pressure reading that will be responsible for that specific movement on the scale. So this is how it looks physically, the Bourdon tube. This is the opening that is connected to the process, this part of it. So as the pressure increases, okay, this Bourdon tube will stretch. As it stretches, this spindle will be moved. And remember, we have the scale here, as you can see on this on the far right of your screen, okay? So as the pressure is increasing, you see the tube is stretching out, and as it's stretching, the spindle will move to register the pressure, okay, that is responsible for that stretch. Then as the pressure also reduces, you see it falling back. Are we getting it? So this is the Bourdon tube, how it works. It's a very simple pressure sensor. Very simple and very reliable, okay, pressure sensor. So this is also the Bourdon tube, and then we have it on the gauge already, okay? So the Bourdon tube is inside of this gauge, and then we see the calibrated scale. Are we getting it? So the range of this particular meter is about 10 bar, okay? So as the pressure is increasing, the Bourdon tube is stretched. This will now be moved, okay, to register the pressure that we have on the process. So it's a very simple but reliable pressure sensor that we often use in our process. So the other one that we are going to be looking at, or ones that we are going to be looking at, are the diaphragms, the capsules, and the bellows. Okay. So the diaphragm basically they are made up of a very light membrane that is capable of stretching. Okay, when subjected to high pressure, it's just like the diaphragm that is separating the thorax from the abdomen in humans. Okay, as you increase the pressure in your thorax, that is in your lung, the diaphragm will stretch. Okay, it also uses the same principle. So as you can see here, as the pressure increases, this part of it is exposed to the process. As the pressure increases, it stretches the diaphragm. Okay, as it stretches the diaphragm, that diaphragm movement is now transmitted into this element, okay, that will eventually cause the movement of this spindle. Are we getting it like we saw earlier? But instead of the process fluid directly affecting the stretching, it is this element, okay, that got its movement from the diaphragm. So if it stretches, it moves up. Once it's collapsing, it moves down. That is what we are seeing here. Okay. So as the pressure is increasing, it stretches, moves up. Okay. As the pressure is reducing, it collapses, move down, and then that will affect the movement of the spindle on the gauge. So we also have the capsule. The capsule is like two diaphragm, okay, one on top the other. Are we getting it? As you can see on your screen, this is one diaphragm, this is another diaphragm. Have the edges sealed. Okay, one part, the lower part of it, or one part of it is exposed, have an opening that is exposed to your process. Then the other part is attached to a lever or something that will carry the movement of the upper diaphragm, okay, to your gauge, as we saw in the case of this diaphragm, this capillary, okay, that drives it. Could be fluid also. Are we getting it? Fluid could be contained here. So as this one is stretching, it increases the pressure here, and that fluid can transmit the pressure to this part of it. Could also be a bottom tube that can cause the stretching here. Okay, so here we have two of such a diaphragm. So as the pressure increases, the diaphragm, the capsule is inflated. Okay, and then as it's inflated, it rises, as we saw the other time. You see, it rises, and then it moves the spindle on the indicator, as we saw in the case of the diaphragm. Okay, so once the pressure in the capsule has increased, you see this movement here. The spindle is attached on the indicator, okay, and then that gives us or register the pressure. So the capsule is another very simple pressure sensor. So we have the here, as you can see, pressure. This is the capsule, stretches, okay, and then this the mechanical or mechanism, and here we have the dial in the front, and then we have this is the gauge, so to say. This is what we are discussing, okay. So we have the capsule here, then the capillary that sends the movement of the capsule to the gauge, okay, and then as the gauge moves, it registers the pressure that is exerted in the capsule. So we have the bellow. As you can see, the bellow is just like a convoluted structure, okay, that is capable of expanding once a pressure is exerted to the internals of the bellow. That is what you are seeing here. So as pressure is exerted, you see it stretches. Okay, it opens up, stretches out. So and then since we have the spindle attached to this lever that is attached to the bellow, so as the pressure increases, it moves up, and that is registered on the spindle. That is what we have here too. Okay, so the pressure increases, stretches the bellow. That bellow movement is transmitted to the movement of this spindle, and thus we have the pressure on the line registered on the pressure. So these are very simple pressure sensors. Okay, so we have another reliable pressure sensor, which is the strain gauge. Okay, the strain gauge. The strain gauge is usually made up of a very thin wire material, thin material, and we know that resistance of a wire is equal to rho L over A, where rho is the resistivity of the wire and L is the length of the wire. A is the cross-sectional area of the wire. Are we getting it? So now, on the strain gauge in the sensor, the L is fixed, as you can see on the right. The length of the strain gauge is fixed. Okay, so as you exert pressure into the strain gauge, you see that the strain gauge is capable of stretching. Remember, the length is fixed. As it's stretching like that, it thins out. Okay, so as it thins out, what do you think will then happen to the resistance of the strain gauge? Let's look at the formula again. R is equal to rho L over A. So as it's thinning out, what happens to A? A is reducing. Okay, so when you look at that relation, R is equal to rho L over A, it means that the resistance will do what? Will increase. Are we getting it? So this strip of wire, this strain gauge, is connected to a Wheaton bridge. At no pressure, we have the zero voltage out. Okay, remember our Wheaton bridge experiment with the galvanometer while in secondary school or college. Okay, high school, I mean to say, not college. So the Wheaton bridge experiment. Okay, so you see that it is calibrated such that all of these resistance selections, okay, they are done. Remember, this is it. Okay, all of these resistance selection, they are done such that the output from here is okay, the output from here is zero when you have your normal supply voltage, which is this excitation voltage, as you can see here. Okay, so once it is stretched, you see that the balance on the Wheaton bridge will be affected. Okay, because this resistance have changed or increased, so that will cause voltage to flow at this. So the amount of voltage that will flow here depends on the change that we have here. Okay, so you see that the meter reading will be calibrated to give us a direct reading of the pressure that will cause that change. Okay, so this is an example of the sensor. Here is subjected to the here is connected to the process. The process fluid stretches the diaphragm. Okay, we have the Wheaton bridge, the power supply and the outputs, they come in through these cables. Okay, and then this is fed into the system that will give us either a direct reading or for control purpose. Okay, So these are pressure transmitters. The pressure transmitters, what they do is that they receive signals, okay, from the sensor that is on the line. Okay, see, this is an impulse line. Okay, okay, the sensor is here. Okay, receive signal from the sensor, and then it amplifies it. Are we getting it? And then transmit it to. So it is what we now amplify it to this 4 to 20 milliamp value that will be transmitted either for control or for monitoring purposes. Okay. So the transmitter is basically an amplifier and a transmitter, so to say. It amplifies and sends the result, the amplified result to where that result will be used. So these are examples of pressure transmitters. Okay. So in most designs these days, we have both the sensor and the transmitter in a single transmitter unit. Okay, like we have here. Okay, this is a DP. We'll see it later. Differential pressure transmitter. Okay, so this is the impulse line that is subjected to that brings the process fluid, and the pressure on this line is the same with that in your process. Okay, so these are wireless transmitters. As you can see, these are transmitters with wire, okay, that can send the 4 to 20 milliamp signal to your controller or to your control room, as the case may be. So here is a complete configuration of the process, the pressure sensor here, okay, the transmitter that sends the signal to your controller, then your controller to your final control element, which is the valve. Okay, so it is basically to, this one is basically to control flow, and as the flow is controlled, the pressure is monitored. If the pressure is high on the upstream, that is upstream this valve, okay, flow could be increased to reduce this pressure. Are we getting it? So this is a pressure switch. Pressure builds up to a stage. The switch is energized, okay, and then the valve is meant to open up. So this is a transmitter as you are seeing on your screen. Okay. So the next process variable that we'll be looking at now is temperature. Temperature is also a process parameter that could change with changing operational condition in our process. So what is temperature? Temperature actually is a measure of the molecular energy, okay, of the process material, process fluid that we are looking at. That is the heat energy that is contained in the process, or the potential of the process to transfer heat, or the process material to transfer heat. So this is one of the most, in fact, is the most measured variable in process industry. So we have basically 4 temperature scales. 2 of them are the most popular, that is the Fahrenheit and the Celsius scale. We also have the Kelvin scale and the Rankine scale. So this Celsius scale and the Fahrenheit scale, they are the most popular temperature scales in the process industry today. So in the Celsius scale, you see that the boiling point of water is 100 degrees Celsius. Okay, and then the freezing point is 0, and that corresponds with 212 degrees Fahrenheit for boiling point and 32 degrees Fahrenheit for the melting point or freezing point of water. This variable temperature, we have different sensors that we can use to monitor temperature. Okay, so we have sensors that uses expansion fluid or expansion devices. An example are those fluid or materials when heated, they tend to expand. Then when they are cooled, they contract back to their normal state or normal position or structure. Okay, so here are some examples of fluids or liquid that could expand when heated. We have mercury, we have alcohol, and we have pentane. So all of these, they are used in the mercury in glass thermometer. So this is the mercury in glass thermometer. As you can see, this is the bulb containing the mercury. So once you heat up this bulb or make it to come in contact with whatever temperature, whatever body that you want to measure the temperature, you see that it will absorb the heat and it will start rising through the stem. Okay, so you see some calibration on the stem. So these calibrations, they've done to give us a direct reading of the amount of heat or temperature that can cause the rise of that mercury along the stem. Okay, so this is one temperature sensor, which is a temperature thermometer. It's called thermometer, and this is the clinical type thermometer that is used mostly in the clinic for medical purposes. And this is what you have here. You have the expanding liquid, okay, or the liquid that is capable of expansion in the bulb. So once the bulb is heated, it will expand along the stem. So the height to which it gets to is calibrated to give us a direct reading or give us the temperature of the body that we are actually measuring. Okay, so in some we have the alcohol and the others we have the pentane. So as you can see, they have different range of temperature for which they are very, very effective. So if you look at the mercury, is between 35 and 510. Okay, you can comfortably or conveniently use to measure temperature within those range. Then the alcohol -80 to +70, and then pentane -200 to +30. Okay, so you see that this kind of thermometer is fitting for cryogenic area or cryogenic process. Okay, so also is the alcohol to some extent. Why a process that is very hot, this could give us a more reliable reading, that is the mercury in glass thermometer. So we also have other types of sensors apart from those that uses expansion liquids that are capable of expanding. We have the one that uses expansion devices or materials that are capable of expanding as they are when heated as their sensor. Okay, so an example is the bimetallic strip or bimetal. So when you say bimetal, we are talking of two dissimilar metal that have different thermal conductivity joined together. Okay, so you see, as in this diagram, since they are separated, when you subject them to the same amount of heat, okay, delta T, you see that one is capable of elongating or extending more than the other. But once they are joined in the middle, okay, you see that it is no longer possible for the metal on top to extend more than the red, that is the red one now, to extend more than the blue. Okay, so that will cause a bending effect on the metal since they are bonded. Okay, so this is an example of what we are discussing. So this movement, this bending movement or this displacement correspond to a certain level of temperature rise of the bimetal. Okay, so this could be calibrated on the temperature scale to give us a direct reading of the temperature that causes that movement. So here we see an example of it. Okay, so you see, once it is subjected to heat, the sensor, which is the bimetal, it will expand. As it's expanding, it causes the movement of the pointer. Okay, and it can move either to the right as the temperature is increasing, and to the left as the temperature is decreasing, to give us a direct reading of the temperature that is causing that movement. So these are the example of the thermometer gauge, temperature gauges with the bimetal that is in this sensor or in this area that is attached directly, okay, into the process. So here I have a direct contact with our process. As it's heated up, the bimetal in it will elongate, and that will cause the movement of the temperature gauge. So let's assume that this one is in the process now. It shows here that the temperature of the process is about 20 degrees Celsius. So this is a form of sensor that could be used to look at the temperature in our process. Okay, so this is temperature sensor. So we have another type of temperature sensor, which is the resistance temperature detector. Okay, so the resistance temperature detector, it actually uses as a sensor materials whose resistance will change as the temperature of the material is changing. Okay, that is, if it is one that is having positive coefficient, the resistance of the material will be increasing as the temperature is increasing. If it's one that have negative coefficient, as the temperature of the process is increasing, okay, that is the process that is looking at, as it's increasing, the resistance, okay, of that element, the sensing element, the sensor, will be reducing. So here we have an example of it. So you see the resistive material, it is made up of a platinum, okay, platinum wire. So this platinum wire, once it is heated, the temperature will do what? It will change. So you see the range of temperature that you can use, it very wide range of temperature, from -258 from the cryogenic region to very high temperature of about 727 degrees Celsius or centigrade. Okay, so here, since the resistance is changing with the temperature, so how do we harness this variation to give us a representation of the temperature of the process that we are looking at? So you see that the RTD, or the resistor temperature detector, is connected to a Wheaton bridge. Are we seeing it? So at rest, that is at zero temperature, it is connected so that the deflection or the output from here will be 0. Okay, so as the temperature is changing from 0, of course, the balance of the Wheaton bridge will be altered because the resistance of the RTD will change. So let's assume that it's a positive coefficient RTD. As the heat is increasing, the resistance will go up. So as it's going up, the balance here will be altered, and then the output from here, the voltage that will be generated, that will come out from here, okay, from the Western bridge will be going up, okay. So it is now fed into a meter that has been calibrated to give us a direct temperature reading of the process. So here is the RTD. Okay, we have the RTD, which is the sensing temperature sensor now, the sensing part. Okay, you can see it at the tip. Here we have the RTD. Then the connecting cable runs out, okay, into this junction box, which will be fed to your transmitter that will later amplify it and send it to wherever you want it to go. So as here is having contact with the process, as the temperature is changing, the resistance of the RTD embedded in it, okay, will be changing. Since it is connected to the Western bridge that is here, that imbalance that will be caused will cause the generation of voltage, and that voltage will be sent to the transmitter for amplification or sent to your local gauge or to the control room to give us the representation of the temperature or a reading of the temperature in our process. So this is how it is connected in the feed. You see that the RTD is connected into the process. It has a direct contact with the process. Then the sensor wire, okay, is run to the junction box, and from the junction box it is connected to your transmitter or to your controller, okay, and there it could be amplified and sent to wherever it is sent to. So this is another form of sensor, the resistance temperature detector. So what you should put at the back of your mind now is that the RTD or resistance temperature detector uses a sensing element whose resistance changes with changing temperature. Are we getting it? So as the temperature is changing, the resistance is changing. So that resistance forms a section or a leg of the Western bridge, okay, that could alter the balance of the Western bridge as the resistance is changing, and that can cause the generation of voltage, okay, whose magnitude is dependent on the magnitude of the temperature that is that the RTD is exposed to. So we also have another type of the temperature sensor, which is the thermistor. The thermistor also have the capability of changing resistance with changing temperature, okay, and like the RTD, as you can see here, since the temperature varies with since the resistance varies with temperature, we can also use it to form a leg of the Western bridge, okay. So the thermistors, they are basically semiconductors. They are metallic oxides, okay, and they mostly have negative temperature coefficient. That is, as the temperature is increasing, the resistance of the thermistor goes down, okay. So they have high sensitivity, and that is why you see them mostly in electronic circuitry or processes that need high sensitivity, that are not too harsh for thermistors like this, okay. So they have very high sensitivity, which can build up to 10% change in resistance per degree Celsius. So the thermistor, they are the most sensitive sensors, the most sensitive temperature sensors available today, okay, the thermistors. So the thermistors, they have very short response time. That is one of their advantage, from between 0.5 to about 5 seconds. Okay, they can respond to change in temperature at that very short time. And they can operate between minus 50 degrees Celsius to about 300 degrees Celsius. So the thermistor, like the RTD, they change, resistance will change in temperature, but they are mostly uh, negative coefficient sensors. Okay, they can also be positive coefficient too, which means that their resistance could also rise with increasing temperature. Other sensor for temperature that we are going to be looking at is the thermocouple, that is very common also in the process industry. The thermocouple, I think, is the most popular, okay, in the process industry. So, like bimetallic strip that we saw the other time, they are made of two dissimilar metals too, okay. So these two dissimilar metals, when you join them at both ends and subject those two ends to different temperature, because of that difference in temperature, you see that the electrical charges will be made to flow. So the magnitude of these electrical charges or electrons that flow is dependent on the difference between the temperature of both ends. Okay, so the higher the difference, the higher, the greater the charge that will flow through the thermocouple. Okay, so which means that one end of it is which is the reference point, is the cold end, and the other end is the hot end. Okay, that is the side part that you subject to the temperature that you want, which means this part of it will be in contact with your process and this part will be out of your process. So this is what we are seeing here. So that charge could be read by a voltmeter. Okay, that charge could be read by a voltmeter, and then that voltmeter is connected in line, okay, with one of the conductor. That is, the conductor is broken and then connected in line with it, okay, to the cold end. So this part that is in contact with your process, and this is the cold end now. So as the temperature is increasing, you see that the amount of current that will be flowing or voltage that will be induced here will also increase. Okay, so here we have an example of it. You see, as you are hitting the temperature, the voltage in millivolts that will be generated will go up. So this is the thermocouple, and this is the junction box that carries these two. Okay, this is junction box where we have these two terminals, okay, that you can connect to your controller or to your transmitter. So this is how you see it physically, the thermocouple, okay. So the two dissimilar metals, they are here, and this is the two wires, okay, that takes your output voltage to your transmitter or to your controller. So this is how it is connected physically, installed physically in your process. You can see we have different thermocouples, about 3 thermocouples connected in this point of the process. Okay, so here we have the output taken to our controller or transmitter. So this is an example of what we are talking about. Okay, so once you subject this end to increasing temperature, you see that the voltage output will be changing. Okay, as you are increasing, the voltage output will be changing. So like in this case now, you see this meter gives you a direct reading of the temperature to which this thermocouple is exposed to, and that is what we are seeing here, 66.7 degree Fahrenheit, which is about 17 degrees, between 15 and 17 degrees centigrade. Okay, so that is what we also have here. So this meter is taking the place of this. Okay, and that is what this gauge is doing here too. It's taking the place of this meter or this meter. Okay, so this is the physical one that we have stored in our process. Here's another example. So this is it too. So this is where we have the thermocouple connected to, this is the transmitter. Yeah, indicator, it indicates the temperature of the process as read by the thermocouple and could also transmit. Are we getting it? That to either our control room or to the controller in the process to do whatever control that you need to effect within the process. So next we are going to look at another process variable, level. Okay. So when we say level, we are talking about the level of fluid or the height of fluid in a vessel, in a container, in a tank. Are we getting it? So that is what we are actually looking at. So the height of fluid in a vessel constitutes level. So there are some process operations, okay, that level measurement and control is critical for us to get our desired product or our desired output. So we have different method of measuring level in the process industry. We have the direct and indirect measuring method, or the manual and the automatic level measurement method. Okay, so let us look at it from the angle of direct sensing and indirect sensing measurement. We also have the single point measurement. So as you can see on your screen, you see this is a manual gauge. See the sight glass, okay, that gives you a clear indication of the level of fluid in this vessel. So as the fluid is rising, okay, the connection is done such that as it's rising, the pointer or the indicator on the side glass will also be rising to give us a clear indication of the level within the vessel. So that's the manual. We also have other manual type of level measurement, like the, as we will see later, the physical gauging, okay, by using either a dipstick or a dip tape. Are we getting it? To get a calibrated stick or tape, okay, to get the level of the fluid in the vessel. So we have other automatic measurement. We have those that transmit the radio frequency, okay. The radar system also transmits radio frequencies. Then we have the ultrasonic level detector, the magnetostrictive level detectors, okay. Then we also have differential pressure level detectors. Are we getting it? Okay. All of these, the thermal, the vibrating tuning fork, the thermal dispersion, the float switch, which is also a manual or a direct sensing method. Okay, all of these, they are different methods that we can use to sense the level of fluid in our vessel or in our process. So let us look at some of them in a little bit details now. So this is the direct sensing method, which is the sight glass. So as you can see, the sight glass, you see that the sight glass work with the principle that the level of the fluid, since we have this sight glass or this column connected directly, okay, to the main vessel, you discover that the level of fluid in the vessel will equal the level of fluid on the sight glass, okay. So that will mean that this level indicator, its position will give us a direct reading of the position of the fluid in the vessel. That is what we are seeing here. You see the position of the fluid, okay, in the side glass. So that gives a clear indication of the position of the fluid inside this vessel. So by merely looking at the side glass, you see that you know the level is here. So when you extend, the level should be about this position. So this one could be calibrated too, okay, to represent this particular the height of the vessel. So if you say maybe let's assume it's 2 feet here now. If it is 2 feet here now, 30 centimeter here, then here will be calibrated 30 centimeter. Or if here to here, the bottom to the top, bottom to up of this vessel is say 100 centimeters as an example, okay, or 30 inches. Here to here will also be 30. That's from here to here will be 30 inches. So here is calibrated to give us the various readings within that 30, that is between 0 and 30 inches. So if here is showing us that it is say 8 inches as an example now, okay, if here is 8 inches, it means that the fluid is at that level 8 inches within the vessel. So that's a sight glass, and it's a direct sensing method. Gives you a direct reading of the level. Another direct sensing method is the float. Okay, so you see, since this is a float, as the level of the fluid is rising, the float will be rising along with it. Okay, so you see the connection as it's rising along with it. This will be dropping to give us, if especially you can see like here now, will give us the direct reading on this calibrated scale. Okay, as the float is rising, this is dropping, which means the calibration will be from up down. Are we getting it? So when it is full, the scale, the calibration, it will move down the scale of this calibration. This is another float. Okay, so as it's rising, you see that the spindle will move to full. Then as it's going down, the float will be falling and it will move to this end. Okay, when it is 1/4 full, half full. This is a clear example of what we have in our vehicle fuel tank. So this is another form of direct sensing method. So other forms, as we said earlier, is the dipstick. Okay, so most of our oil gauges use dipstick. So as you dip, you cock, you see that the level to which we have the oil or the fluid in the vessel will be marked on the dipstick. So since the dipstick, either if it is calibrated, it will give us the level reading. If it is not calibrated, maybe we have the range, okay, that we expect to, that is the low and the high. Okay, so we expect to be between low and high. So that will also give us an indication. So this is another example of a dipstick that is used on a drum. Okay, as you dip it, the level of the fluid in the drum will be marked, or the dipstick. So here we have another example that is used to measure directly the level of fluid or liquid in a tank. It's also the dip method, which is the dip tape. Okay, so here we have the plumb ball, which is a weight. Then this tape is calibrated. So the mark on it, together with the length of this plumb ball, will give us, as you pull it out. When you pull it out, you see the mark on it. Will give us a direct reading of the level of the fluid in the tank. So in doing this, you you need to go up the vessel, the tank, to carry out these measurements. Are we getting it? So these are the direct or manual level sensing or gauging method. So we also have the indirect method, okay, which means you convert one process variable, there is another process variable, you convert it to level. And a very notable variable that we can convert to level is pressure. Okay, remember, in a vessel, the pressure that the vessel exerts at the base of the vessel is dependent on the height of that fluid in the vessel. Okay, that is, pressure is equal to rho g h. Okay, where rho is the density of the fluid in the vessel, then g acceleration due to gravity, and h is the height. So since the rho and g, they are constant, as h is varying, what will happen to the pressure? They will be varying, and h is the height or level of the fluid in the tank. So as the pressure is increasing, that shows that at the base, the pressure is increasing, that shows that level or height is increasing. As it's reducing, that shows that level or height is reducing. So by measuring the pressure at the base, okay, we can use it to infer that is, deduce the level of fluid in the tank. So this is a DP, differential pressure transmitter. Okay, so one end is subjected to high pressure at the base, and the other end is subjected to low pressure at the upper part of the tank. So whatever that is given off from the transmitter is directly proportional to the difference that is here. So as the height is, if the level of the fluid in the tank is high, you see that the differential pressure will be high, because the HP side will be high and the LP side, which is almost constant. Then as the level is going down, HP side will be coming down. Okay, so the signal that will be given off will be dependent on the level or height of the liquid in the vessel. So that is the indirect sensing. That is, we are using pressure now to infer the level of the fluid in our vessel or in our process. So this is an example of the installation of a level gauge, okay, using differential pressure transmitter. Are we getting it? So whatever that is sent off this, okay, wherever it will be read off, okay, on the indicator here, it has been calibrated to give us a direct level reading of the fluid in the vessel. So we also have other types of level sensor, which is the ultrasonic level detector. In the ultrasonic level detector, we have a transmitter and receiver in one detector. Okay, so an ultrasound is emitted. When we say ultrasound, we mean sound that is beyond the human hearing range. So that is the kind of sound that is transmitted. So it actually travels with the speed of sound. Okay, so as it goes into the vessel, on the surface of the fluid in the vessel, it is reflected. So the transmitter transmits the ultrasonic wave, so it is reflected back. Okay, so the time it's used to travel gives an indication of the level of the fluid in the vessel. So if the travel time is short, it means that the fluid is the level of the fluid is high within the vessel. Okay, that means the vessel is full. That is why the time it took the the ultrasonic signal to go to the level and back is short. But once the is a little bit empty or is low, you see that it will take a longer time to travel to that surface and back. Okay, so that travel time, which will be deduced by the measurement device, okay, is calibrated to give us a direct reading of the level within the vessel. So you can see how it is physically installed on the process, okay. So as it is emitted, it goes to the liquid surface. I guess this is water. It is reflected back, okay, and then the time of travel indicates the level to which the water is in that container or in that reservoir. Okay, so this is it. The transmitter emits the ultrasonic sound. It is reflected on the surface of the fluid, sent back. The transmitter emits the ultrasonic sound. It is reflected at the surface of the fluid, sent back. So the travel time gives us this the level of fluid, okay, in the tank. So this is how they are physically installed. This is the one that is physically installed in a vessel. Okay, this is an open tank. This is a closed vessel. Are we getting it? So you see the time delay between the transmitted pulse and the received pulse. So this time delay is an indication of the height of the fluid. So we also have the capacitive level detector. So in the capacitive level detector, they are usually mainly used in conductive, that is to determine the level of conductive fluids in a vessel. Okay, so the fluid will now form the electrolyte, okay, within the vessel. So we know that as the electrolyte concentration is increasing, the capacitance will do what will also increase, and as the height is increasing the concentration of that electrolyte between these electrodes, okay, that is now helping to form a capacitive cell. So that capacitance will now be what will be detected and calibrated to give us a direct reading of the level of the fluid in the vessel. So here is an electrode. In this case, since we have single electrode, the body of the tank is used, okay, as one of the electrode. So the principle remains the same. So the next process variable that we are going to be looking at is flow. Flow is another very important process parameter that is often measured, okay, or looked at to control our process. So flow is actually the volume of fluid that goes through a section of the process per unit time. Okay, so how do we measure this flow? We have different method of measuring flow, but the most common method of measuring flow is the one that uses the differential pressure method. Okay, what happens in this case is that a restriction is created in the flow path, and that restriction causes change in fluid velocity. Okay, and that change in fluid velocity causes change in the fluid pressure. Are we getting it? So what that means is this. As you can see, this is assume this is our process pipeline. Okay, you see this restriction is deliberately created on the flow path. So this is an orifice plate with an opening. We'll see how it looks like later. with an opening in the middle. Okay, so the fluid that is coming at a particular velocity on impinging on the orifice plate, it's a kind of slows it down. When you apply Bernoulli's principle, the pressure will go up once you apply Bernoulli principle since the velocity is coming down. So as you throttle, the velocity will go up. Okay, when you apply the same Bernoulli's principle, the pressure will do what? Will go down since the velocity is going up. Okay, so that change in pressure across the orifice plate is what we use to deduce the flow rate. Okay, so the higher the differential pressure between the high pressure side and the low pressure side, the higher the flow rate of the fluid across that orifice plate. So this is the representation of what we just discussed. So the lower volume, the lower velocity causes increase in pressure. Okay, as it goes through the orifice plate, the pressure reduces. So this pressure differential, okay, is determined by the flow rate. So the higher the flow rate, the higher this pressure differential. So that is what we use to deduce the flow rate across the orifice plate. So that is what we have here now. So this is the low pressure side, this is the high pressure side, okay, across the orifice plate. So you can see 80 psi, 66 psi. If you increase this flow rate now, you'll see that this will go up this way. That is the differential between both of them, okay, will be high. So the pressure is going up on this side, okay, while the velocity is coming down because of the restriction. Then as it's throttled, the velocity will go up while the pressure will come down, okay, on application of Bernoulli's principles. So this differential pressure, okay, could be fed to a transmitter that will give us a direct, that has been calibrated to give us a direct reading of the flow rate. So that could be sent to a controller that is sent to the final control element that helps us to control that flow rate in case it is not the flow rate that we actually want in the process, either to reduce or to increase that flow rate. So this is the orifice plate that we are talking about. This is how it looks like, and it is installed on the line between the flanges, as you can see. Okay, this is it. So the beveled end is made to face the downstream end of the flow. Are we getting it? So this is another example of the flow meter. This part is connected to the upstream. This part is connected to the upstream, as you can see by this direct arrow. And this part is connected to the downstream. Okay. So as the flow is increasing, the differential pressure across will be increasing, and that is converted to a direct flow reading on your flow meter. So we also have other types of differential pressure flow meters. We have the pitot tube. Okay, we have the pitot tube, and we also have the venturi tube. Okay, so what they also do is to find a way of creating pressure difference along the stream and measure that pressure difference. So like in the previous case with the orifice plate, the pressure difference increases with increase in flow. So let's take the example of the pitot tube now. So you'll see that here helps us to measure the static pressure, which is like this end of the differential pressure meter. Okay, so here helps us to measure the static pressure, which is here, Then here we'll be looking at the dynamic pressure. So which means that as the flow rate is increasing, you'll see that the pressure on this tube, okay, in this tube I mean to say, will also be increasing. And you see that will increase this leg of the manometer. So the differential pressure, you see it will be going up as the pressure is increasing. So these two legs, okay, could be connected to a differential pressure transmitter, and that will help us to look at the pressure on the line. So like in the case of the differential, the case of the orifice plate, orifice meter, you see that as the flow rate, flow velocity is increasing, which is the flow rate, you will see that the differential pressure will also be increasing. Okay, so the static pressure will remain constant, and as the flow is increasing, since this the flow velocity does not have much effect on the static pressure, you see that the dynamic pressure will be getting up. Okay, so it will rise to a stage that will now uh, come to the stagnation pressure. Okay, and the pressure will just be steady at that end. So that is the dynamic pressure. Is the stagnation pressure is the sum of this static pressure and this dynamic pressure. Okay, but the difference basically is determined by the flow rate in the pipeline. So this is an example of a venturi tube. Okay, so you see the tapered end. This is the tapered end. So it's just like this end now. Remember, our goal is to create a restriction on the flow. Okay, as you do that, then the flow velocity will momentarily reduce. That will make pressure want to go up, which is indicated on this leg of the impulse line. And then as the flow is throttled, the velocity will increase, and that will reduce the pressure. So this differential, this pressure differential, okay, caused by the venturi action, is actually determined by the flow rates across this section of the pipeline. So that is what we have here. You see the two impulse line taken to your flow meter, wherever it is, and this is it. Okay, so here from the high pressure end, okay, and then this from the low pressure end to your pressure transmitter that is wired to your controller or your control room, and to your control room or controller, and then to the final control element, which is the control valve. So this is how it is installed in the field. This is the pitot tube type of a flow meter. Okay, so like the pitot tube, it does not create that restriction, so there is no pressure difference as we saw here. But there is a drawback. If the fluid is contaminated, that can, by debris, that can cause plugging of this high pressure end, okay, of your pitot tube meter. Okay, so the next that we are going to look at is the magnetic flow meter. So the magnetic flow meter actually uses the law of electromagnetic induction. We all know from Faraday's experiment that if a conductor moves through a magnetic field, an electric current is induced in that conductor. Okay, so in this our case, the conductor now is the fluid, which means the implication of this is that the fluid must be conductive for us to be able to use our magnetic flow meter. Okay, so we'll say the magnetic field created by this permanent magnet. These are the magnetic lines of fluxes. So as the fluid is flowing through, you see these electrodes, okay, the fluid will momentarily at that point complete the connection, and since voltage or electric current has been induced in it, it will run through this circuit, because it will at the end of the day close the circuit, and then you have your reading. So the rate of that induction of the electric current, okay, is, or the magnitude of induction is determined by the flow rate. So the higher the flow, the higher the amount of induced voltage on this circuit. So with that, we can calibrate the flow meter, okay, since it's getting voltage signal, to give us a direct reading of the flow of the fluid through that section of our pipeline. So that is what we are seeing here too. So as you can see, you see this is the conductive fluid that is flowing through the section of the flow meter. So you see, as the flow is increasing, just watch what happens to the flow meter. You see that the voltage induced, the voltage induced will be increasing. As the flow reduces, the voltage induced comes down. Okay, so which means that we can calibrate the voltage that is induced here to give us a direct reading of the flow rate of the fluid through that section of the meter. So this is an example, physical example of the flow meter. This is how you see it, and this is one that is installed in the feed physically. Okay, so like this flow meter now does not place any restriction on the flow path of your fluid. Are we getting it? But the fluid must be a conductive fluid. So in most cases, they apply them for slurries and conductive fluid, which means we cannot use it to measure the flow rate of non-conductive fluids like hydrocarbon. Okay. So the turbine flow meter is what we'll be looking at next. The turbine flow meter actually have a section has turbine in it. Okay, so this turbine, it has a set of blade which can rotate when it is impinged upon by the fluid that is flowing through this section of your pipeline. Okay, so this is the flow conditioner to help us to have as much as possible laminar flow. Okay, so directing the fluid onto the blade. Are we getting it? So the between these two blades, a specific volume, okay, would have passed this section of the flow meter. So what this is a pulse counter, okay? So what this pulse counter does is that it counts is a pickup anyway. It counts the number of times each of these blade pass through it. So when each blade pass, it generates a pulse. When each of the blades pass, it generates when another blade pass, it generates another pulse. Okay, so the number of pulses compared to the unit, that is the time that it takes for those pulses to be generated, will give us the flow rate, the volumetric flow rate. Remember, we said between two pulses, a specific volume would have passed through the turbine flow meter. Okay, so let's say between two pulses, we have 2 liters would have gone through the turbine meter. A pulse. So if we have, that is a pulse now, between two pulses makes a pulse now. So if we have 10 pulses, it means that we have 20 liters of fluid, okay, gone through, that means 20 liters of fluid have gone through that section of this section of the turbine. Okay, so the time it takes for us to generate that 10 pulses, assume is 5 seconds. Okay, so that means we'll have 20 over 5. Okay, that will give us 4 liters per second. So that will now be the flow rate through that section of the turbine. So in the turbine flow meter, we have turbine, okay, in it that turns when it is impinged upon. That is when the fluid flowing through the pipe strikes on it, it turns it, okay. So the volumetric flow rate increases, okay, that is the number of pulses, like we said earlier, increases with the flow rate across this section of the pipe line, okay. So this way, at the end of the day, give us the volumetric flow rate. So these pulses that is sent to the meter now, or the transmitter, they give us a direct reading of the flow rate, putting into consideration the number of pulses and the time it took. So the calculation is done here, okay, saving us the stress of doing it manually. So that is what you are seeing. So as you watch, you see that as the flow rate is increasing, what happens to the signal? You see that it is going up. Are we getting it? So this is an example of the flow meter now, okay, the turbine flow meter. We have the turbine in here that helps to generate that pulses that is picked up and then converted to flow rate in the flow computer, okay. So the next flow meter that we are going to be looking at is the coriolis flow meter. The ones that we have considered so far, they are volumetric flow meters, okay. But the coriolis flow meter helps us, it's a mass flow meter, helps us to determine the mass of fluid that have gone through a section of the fluid. So this is the coriolis flow meter, and the coriolis flow meter, they work with the coriolis principle. That is the effect that a moving mass will have on a body in a rotating frame. So if you look at this coriolis flow meter, it has a U section. Are you getting it? Inside this U section, we have dual parallel flow tube. So the fluid does not go straight across. It is made to go through those dual tube, separated into two equal quantity or equal volumes, okay, or equal mass as the case may be, and made to go through the tube, as you can see here, okay, before it is discharged downstream. So how does this flow meter function? So in this flow meter, we have a drive coil, okay, that helps to oscillate those two tubes, that create a vibrating force on those two tubes that makes the tubes to oscillate. Are we getting it? Then we also have an input and an output sensor, okay. So the drive coil or the signal generator is here. Then we have input. If this is the upstream end, we have the input and we have the output, okay, sensors. So how does it help us to measure the flow through this section? Now, ordinarily, when there is no flow across this, that is across through the tubes, okay, when the drive coil is energized, you see that those two tubes within this section of the flow meter will be vibrating. Are you getting it? So as they are vibrating, you see that the vibration is not distorted, so to say. So at this stage, as we will see later, the signal that will be picked up by the input sensor and the output sensor will be in phase. Then when we start the flow of fluid through the meter, what will happen is that that mass movement of the fluid, okay, through the tube will have that coriolis effect or twisting effect on the tube, as you can see in this second diagram. So you see that this the movement of the tube or the oscillation of the tube is not as smooth or as straight as that of the first one. You see the twisting effect, okay, on this tube. Are you getting it? So because of this twisting effect, we will now have a phase shift between the input signal and the output signal of the sensors, as we'll see later. So this is the drive coil, okay? These are the sensors, okay? This we have the, if the flow is from right to left, okay? This will be the input coil, and this is the output sensor. I mean to say, this is the input sensor and this is the output sensor. So since we already have flow, you see that that coriolis effect will cause that twisting of that tube, of those tubes, I mean to say, and that will cause the displacement of the signal generated or sensed at the input coil and the output coil. So that difference, the phase shift, is what we are interested in, because that shift is determined by the flow rate. As you increase the flow, the shift will be increased. Okay, so we have the mass flow rate, okay, of the fluid, okay, registered on the meter. So this is what we have here. Remember, as it is oscillating, as we saw earlier, okay, when there was no flow, you see that the oscillation is smooth, which means there is no shift between the input signal and the output signal. Are we getting it? The output pick up signal, okay? So they are in phase. You see it, crest to crest, trough to trough, so they are in phase. But once there is flow, you see the coriolis effect causing the twisting of the tube, as you have here, okay? You now see that phase shift. See it, trough to crest, trough to crest, okay? So that phase shift is determined by the flow rate, and that is what we have here, okay? So delta T, this is the shift, okay, gives us an idea of the flow rate, okay? So the shift is between the input signal and the output signal, the input signal and the output signal. So there is another quantity that we can also infer or measure from this meter, or with the use of this meter, okay? And that has to do with the observed frequency. The observed frequency, okay? That is the number of oscillation per unit time that you see. So you see that if the fluid is dense, heavy, the frequency will be low, okay? Because it will take greater force. Are you getting it? To oscillate, so the oscillation will be slow, and that will reduce the frequency. But if the fluid is less dense, is light, what will happen to the frequency? You see that the frequency will increase. It's just like the mass spring arrangement. Okay, when you have a spring and a mass at the end of the spring, and then you oscillate the spring. So you see that when you increase the mass, the oscillation, the rate of vibration, okay, the movement up and down will do what? It will drop. Since it's heavy, to be slow. Are you getting it? But if it is light, you see it oscillating faster. That is exactly what is happening here. So the tube frequency is inversely proportional to the density. So when we measure these two parameters, the phase shift and the frequency, we have the mass flow and then we have the density. And as we all know, density is mass per unit volume. Okay, so which means that we can calculate the volume from these two, that is volumetric flow rate, okay, from these two quantity. So if density is equal to mass over volume or mass per unit volume, it means that volume is equal to mass over density. So which we can get from, since